各位朋友，大家好，我现在人在杜拜哦，这是我们台湾气候联盟有一个厂叫 Digital Cross Green。那在我们的隔壁呢，其实就是一个叫做核融合的一个展馆哈，核融合。那当然，其实它不见得叫核啦哈，我们翻译出来核，它是就是一种融合的技术，就下一代新的能源。然后旁边呢有一些传统的核能哦，那我就不必谈这个东西，因为我知道。Fusion 跟这个 nuclear 是不一样的，所以我就今天这几天我就敦亲睦邻，他们也来找我们说，哎，你们产业界是不是想要多了解这个？我说是啊，那我们就来进行这样的会谈。Hello, how are you?
I'm good, thank you.
I'm wondering where are you from? What's your name?
My name is Kirsten Haupt. I'm a German national and I work in France for ITER.
Okay, so ITER, I-T-E-R, right? Who is an NGO?
No, it's an international organization and that works on the development of fusion technology for our future.
Okay. So the first question I want to ask her is how long to commercialize? Because we heard lots of news or lots of progress. It seems next year we can use the new fusion. So I'm wondering when can we use the fusion power to our daily life?
Well, to have a cheeky answer first, maybe you're already using fusion because fusion is the process that goes on in our sun. Yeah. I mean, we are here because of fusion. Yeah. Without fusion in the universe, we would not exist. Yeah. And we want to bring fusion on Earth. So already by that, you can see how actually difficult that is. I mean, to create a star on Earth. And so fusion technology, while it is developing really at a rapid pace at the moment, is a long-term project. It's not a solution for tomorrow. It is a long-term solution. So I cannot even tell you when that is going to be commercialized, but it's certainly in the second half of the century.
Okay, but I mean the large scale commercialized to replace just like a hydrogen power. Because I asked some of the people say, oh, Dr. Baum, at least 10 years. So is that right?
Yeah, I mean, it's more than that, you know. So, I mean, fusion is a very complex technology. Yes, we're working on this already since a long time, and the fusion community gets bigger and bigger, so knowledge gets bigger and bigger. But we still have a lot of milestones to pass to actually get to a functioning fusion power plant. But we are on the right track to do that, in particular at ITER, because ITER is the only fusion project at the moment that develops fusion at an industrial scale. That is our goal. We want to research fusion, the fusion technology, to bring it to an industrial scale so that we can really use the outcomes, our knowledge, to then spread it, share it, and commercialize it, as you said.
But I'm from Taiwan because some people think the fusion is is another nuclear. But by my understanding, it's totally different. Can you make a general explanation to the audience in Asia or the other country?
Sure.
Yeah, please.
Sure. I mean, you're right. Of course, it's a nuclear energy. It's nuclear fusion.
Nuclear fusion.
It is. But what you are referring to is what I always say, the conventional nuclear technology, and that is the fission technology, right? Fission technology is about splitting big atoms. It's like big atoms, plutonium, uranium, that we split into smaller ones, and then because of a neutron that comes out of that reaction, you have a chain reaction. Fission is completely different. Fission is copying the process that goes on in the sun. What happens in the sun? The sun is practically a big ball of hydrogen and helium. So what happens in the core of the sun is that hydrogen isotopes, the nuclei of hydrogen atoms, fuse into a new element, and that is helium. Yeah, and in the process of this reaction, a lot of energy is being released in the form of a neutron, which is so fast that when it is being released at a fusion reaction here on Earth, it will reach the moon in 8 seconds. That's the type of energy we're talking about. The second product that comes out of a fusion reaction is helium. We all know helium, right? So it's one particle of helium that also carries energy, and we keep that to keep heating the inside of the reaction chamber to the necessary temperatures. And that brings me already to an engineering situation that is very, very difficult to do. What we need to have fusion running is we need to have very high temperatures. The temperature in the core of the sun is 15 million centigrades. But you have a different pressure, different density in the sun, so we need to increase the temperature even further. So what we do in this fusion chamber, we need to have a temperature of 150 million degrees. So the particles that are in there are very, very hot. Now you can imagine that this is very difficult to do. Which kind of material can manage these kind of temperatures? No material. So what we do is we create a magnetic cage to capture the particles inside and keep them away from the walls. And with this magnetic cage, we can keep the fusion reaction inside. This is another technological challenge, because for this magnetic cage, we need to have very strong magnets. How do you make a magnet strong? You cool it down. And at ITER, we cool the magnets down to 4 Kelvin, minus 269 degrees. So you can already see the temperature range that we have in a couple of meters. That just illustrates, it's just one of the illustrations to show you how difficult fusion actually is. And there are many others.
Very interesting. But some people still confused about nuclear. For the fusions is totally different. You do not have any kind of nuclear waste at all, right? It's totally different compared to the nuclear we know right now, right? For example, German is no nuclear, but you propose, the government promote, or your research side project, you start have the fusion. Is that right?
Well, Germany is part of the European Union and as such, of course, part of one of the members of ITER. ITER is a very interesting project. It's made up of 35 countries. Okay. So it's an example of international cooperation on an issue that concerns all of mankind practically. So we have 7 members. It's the European Union plus Japan, China, India, South Korea, Russia, and the United States. And these partners together build the machine. It's also very interesting how this is actually done. Normally, countries with an international project, they pay the money into a pot, and then the organization does what it does with that money. But at ITER, it's a little bit different. At ITER, everybody manufactures the parts that are needed for the machine. So all the 7 members, the European Union and the other 6 countries, they produce the parts for the machine. That creates, of course, a lot of expertise in the countries, but also a lot of jobs, and it also produces a kind of sense of ownership of all of that. It's very unique, this kind of setup. So Europe, as the biggest partner with 27 members, plus the Switzerland is still part of that, and until recently also the UK. They take care of 45% of all the contributions, and then the other countries about 9%.
Okay. So right now the leading about the science and research is from the UK or in US?
No, it's all countries contribute to that. I mean, we have all countries contribute in terms of expertise and knowledge, but also in terms of producing and manufacturing all the components. But in addition, I'm talking about this sort of uniqueness of the project as an international project. We also have cooperation agreements with Australia, with Kazakhstan, and with Canada, who also contribute through these agreements to the project.
Okay. So can you show some about a slide and we can understand? Okay.
I have to go down,
yeah,
right?
You go down, yeah.
Oh, well, let me show
this is the sun.
Yes, but
sun is also a fusion, right?
Is there a pointer? No.
No.
So what you can see here is the work site. The work site of ITER, and in the center there is the 2 big buildings. In the front is where the reactor is going to be built. And you saw already the sun here. Yes, we want to bring the sun down on Earth, right? Yeah. I mean, the energy that is in the center of the sun, that runs our universe practically, we want to bring down.
I'm wondering, sorry.
This is the reaction. Sorry to interrupt. This is the reaction of the... This is a tritium particle, and this is a deuterium particle, and they fuse. Oh. And you see the neutron flying off, and this is the helium particle left over. That's the reaction that we want to do on Earth.
Oh, okay.
All right.
So fusion and climate change.
Yeah. And this is the chamber in which it takes place. It's called a tokamak. Okay. It's a Russian invention. Yeah. Mm-hmm. And it means a toroidal chamber with magnetic coils around it. So these magnetic coils create the magnetic chamber. So this is where it's going to happen. And
how large is it? Because when we know the SMR, just I know that some project in US is very large, about 14 hectares. It's not as small. It's a huge.
Well, the work site at ITER is 42 hectares.
Oh.
Yes. And this chamber, if you just look at the volume, this chamber, the volume will be 1,400 cubic meters. And the plasma volume, plasma is the environment, the heated gas yeah, the hot gas in which fusion takes place, will take up a space of 840 cubic meters. Now imagine how big that is. The inside height is 13 meters. And you will never have more than 2 grams of fuel in there. So you're practically speaking about a vacuum. And that is happening in there. Let me see what else we have. You see, these are the challenges. I had mentioned that already, the temperature range, right?
Very hard temperature.
It's very hot in the center. The magnets on the outside are very cold, 269 degrees. Then, of course, you know, you have to control the magnetic field, and you have to keep, we want to reach a self-heating plasma. That is very important for the development of a fusion industry, for a commercial fusion reactor.
You know, such this kind of 4 items you mentioned, a challenge, is very difficult scientific project.
But this is what I had mentioned when you asked me about the duration. All these all these challenges have to be met, you know, and that's a joint effort of these 35 countries. So, but it is a very complex issue. Okay, yeah. Do you want me to continue?
Okay, I think that's all. That's all. Yeah.
So this is very important. Fusion is very, very powerful. It has a very incredible efficiency, a high level of efficiency. It is a carbon-free source of energy. There's no carbon emission from the fusion reaction, right? I mean, if you see, I mean, it's abundant fuel. Fuel comes from water. Most of it comes from water, so from seawater. One of the fuels we will produce ourselves inside the reactor. This is also part of the research. The safety issue is very important. You had asked about that before, about the waste issues. There will be some waste. There will be unused fuel which will be recycled, and there will also be some low radioactivity. But it is in a range that can be handled in terms of engineering and technology, that it is not such a huge problem. Yeah, and the efficiency I mentioned already, this is absolutely incredible. I mean, from about a kilogram of fusion fuel, you can generate as much energy as from 10,000 tons of coal. Just think about that. It's 5 times more efficient than the nuclear technology we're using today.
Okay, thank you very much. Oh, it's a very wonderful idea, and however, to commercialize takes time, have lots of scientific project and challenge. Yeah,
it is.
Yeah.
But at the moment, as you say, there are a lot of projects around the world, but we are all working together. I mean, it's the public, they are the public projects, the private projects, but we are working together on these solutions, and that is something that is very remarkable.
Thank you very much. Thank you.
You're welcome. Thank you. Thank you for the opportunity.
Yeah,
thank you.
Bye-bye.